So in this podcast, I'd like you to consider this integral and set up a reduction formula to calculate it. So have a go at trying to find the reduction formula, and on the next slide I'm going to obtain it, but try it with pen and paper first. You'll get much more out of doing that. Okay, welcome back. Let's have a look at the reduction formula. Okay, so we want to calculate the integral of secant to the power of 6, and to do this what we're going to do is generalize it to in. So we have a label here, and in is defined to be the integral of secant to the power of n, and I'm thinking of n as perhaps 0, 1, 2, 3, 4, so positive integers or 0. And we're going to be using integration by parts, so it's always worth, if you're using it, writing out the formula. And if we're going to use integration by parts, we have to think, how are we going to split up this integrand? So we could think of various possibilities. One would be to write it as 1 times secant to the power of n, and then we would differentiate this and we would integrate the 1. But if we integrate the 1, we're going to get a theta, and we're not going to get a 1 over theta by differentiating this, so this would take us outside of this class. So I think that would be a poor choice. The next thing you might think about would be to split it as 1 power of secant times secant to the n minus 1, so that's clearly our integrand, and then we would be differentiating this, because if we could integrate it, we could integrate this in the first place. So that would mean we would have to multiply in our new integral by the integral of secant, and the integral of secant is the logarithm of secant plus tan, and that's going to take us outside of this class as well. So the next thing, and this may be the thing you thought of first, would be to write our integrand as sec squared times secant to the n minus 2, because the integral of sec squared is tangent. After all, the derivative of tangent is sec squared, and having a tangent isn't bad because you know the identity that's firmly in your heads, I hope, that sec squared is equal to 1 plus tan squared. So in that way, we're hoping to be able to rewrite this inside this class. So that's what we're going to do, and that's our choice. So let's see what happens. So we're going to differentiate sec to the n minus 2 of theta, and to do that we're going to use the chain rule. So we have the secant to the power of n minus 2, we bring the power in front, we reduce this power by 1, so n minus 2 goes to n minus 3, and then from the chain rule we multiply by the derivative of the quantity that was being raised to the power. The quantity that's being raised to the power is the secant, and the derivative of secant is secant times tangent. So, tidying this up, sec to the n minus 3 times sec is sec to the n minus 2. So we actually have the same power of secant times a tangent. So that's our u prime. So v prime, the quantity that we're going to integrate, is sec squared, and as we've said, that's going to give us tangent. And this is starting to look really good because u prime times v, which we're going to have here, is going to involve tan squared. So let's just write it out slowly. This is our formula for integration by parts for in. U times v is sec to the n minus 2 times tan. So I've just written that here. And then we subtract the new integral of u prime, which is written here. N minus 2 is a number, it's not theta dependent. I take it outside of the integral. And then we have sec to the n minus 2 of theta times tangent, but we have to multiply it by v. That's another tangent, so we have tan squared. And we recall this identity, that sec squared is 1 plus tan squared. Way to help remember this is sec squared is going to always be greater than or equal to 1. So it's 1 plus tan squared. Okay, so now we write that term out again, minus n minus 2, and now we're just going to substitute this into here. So we have the integral of sec to the n minus 2 of theta times sec squared minus 1. That's what tan squared is from this identity. So we've got here effectively two integrals, and they're both in our class because they are both just powers of secant. So we're almost finished. So on the next line, we just rewrite this again, just write it out again, and then we've got two integrals. This one is the integral of sec to the n minus 2 times sec squared. That is sec to the n from the rules for powers. So that is what we are calling in. And then we subtract. We've got a bracket here. And now it's sec to the n minus 2 of theta times 1. So that is sec to the n minus 2 of theta. And that's still in our class. And we've just replaced n by n minus 2. So that is in minus 2. So now, what we want to do is expand these brackets. This is our original integral, which is also here. So we're going to gather those together. And this is minus n minus 2 times in. So we take it over here. It means we're adding n minus 2 of our original integral. And we had one of them here already. Then we write this out again. And now we've got minus n minus 2 times minus in minus 2. So that gives us plus n minus 2 times in minus 2. This is n minus 1 times our original integral. So we just divide by it, and we have that our original integral is 1 over n minus 1 times sec to the n minus 2 of theta times tan theta plus n minus 2 over n minus 1 times I of n minus 2. And that is our reduction formula. And what we see, and this happens quite often with trigonometric functions, is that our reduction formula takes us down the ladder 2 steps at a time. Okay, so what I want to do on the next slide is I want to verify this by differentiating it. Remember, if you differentiate this, you're going to get the integrand. If you differentiate this, you're going to get the integrand with n minus 2 as the power. And if you differentiate this, well, you've got to use the product rule, and it should all work out. So I'll do that on the next slide. If you'd like, you could pause now and try to do that yourself. So on this slide, I want to verify this reduction formula by differentiation. And as said, when we differentiate the integral, remember this just means the integral of sec to the power n of theta. If you differentiate the integral, you're going to obtain the integrand. So here, when we differentiate this, we get sec to the n of theta. And when we differentiate this, we get n minus 2 over n minus 1 times sec to the n minus 2 of theta, because that is the integrand here. And this is the term that is going to require a little bit of work to differentiate. So I've just pulled the 1 over n minus 1 through the derivative here. And when we look at this, we're going to be using the product rule. So we're going to differentiate this first, and then multiply it by that, and then we will take this, multiply it by the derivative of the tangent. Now, we're going to have to write out 1 over n minus 1 a lot of times here, so it's easier, I think, to just multiply both sides by n minus 1. So I have an n minus 1 here, and we don't have that on the bottom anymore on this side. So here, we differentiate this. We pull the power in front. That gives us n minus 2. We reduce the power by 1 sec to the power of n minus 3. And we multiply by the derivative of sec, which is sec times tan. And there is a tan there already, so we get another tan. And that's extremely good because that's tan squared. So we're very happy with this. Then the other term is going to be sec to the n minus 2 of theta times the derivative of tangent, and that is sec squared. And this term here is just the numerator n minus 2 times sec to the n minus 2 of theta. That's not changed except for the multiplication by n minus 1. So now, here we have a tan squared, which we can rewrite as sec squared minus 1. And sec to the n minus 3 times sec is sec to the n minus 2. And here we can just multiply those two terms together, and that gives us sec to the n of theta. This term just sits there for the moment. So now we're going to expand this, and we're going to get sec to the n of theta times n minus 2 from this. But we've also got a sec to the n of theta here. So we've got in total sec to the n of theta times n minus 2 plus 1. And n minus 2 plus 1 is n minus 1. So that's really good because that's exactly what we want the other side to be. So all the other terms must cancel. And from here we have minus n minus 2 times sec to the n minus 2 of theta. And then here we have plus n minus 2 times sec to the n minus 2 of theta. So those two terms cancel. And we see that the reduction formula is correct. This is indeed equal to that. So with a reduction formula, you can always check the formula by differentiating it, and that's what we've done on this slide. So the video started off asking you to calculate the integral of sec to the power of 6, and that's what I'm going to do on the next slide. And if you haven't done that yet, why not try to use this formula to calculate I6, the integral of sec to the 6th? Okay, see you in a minute if you haven't done it. Okay, let's move on. So here is our reduction formula, and as commented already, this takes you down in steps of 2. So supposing that we had n being odd originally, supposing we started with I7, I7 would reduce to I5. I5 would reduce to I3, I3 would reduce to I1. I1 is the integral of sec, and that is something that I think people should know. It's the logarithm of the modulus of secant plus tangent end modulus. So that's how you would do that for an odd power. This video is about an even power, so we're going to have I6, I6 will reduce to I4, I4 will reduce to I2, and I2 we know. I2 is the integral of sec squared, and you know the derivative of tangent is sec squared, so therefore the integral of sec squared is tangent. So all we're going to have to do is integration by parts twice. So I6, we're using n is 6, so here it's 1 over 6 minus 1, so that's 1 over 5, times sec to the 6 minus 2, so that's sec to the 4th, times tangent. That's our first term. Plus, and then 6 minus 2 is 4, over 6 minus 1 is 5, so it's 4/5 of I4, because that's 6 minus 2. Now, on the next line, we just write this term out again, plus 4/5, because that's multiplying all of this. So we open a bracket, and then we just rewrite this formula, but now with n is 4. So we're going to get 1 over 4 minus 1, so that's a third, times sec squared, 4 minus 2, times tangent, plus 4 minus 2 is 2, 4 minus 1 is 3, 2/3 of I2, close brackets. As we've said, sec squared integrates to tangent, so we can just put a tangent in here and then expand everything. If we'd started with I8, what I would suggest very strongly doing, would be to, before we used the formula again, would be to expand the brackets and be careful with the numbers. But at this stage, I2 is doable, so we can just put it straight in. So the integral of sec to the power of 6th is 1/5 sec to the 4th tan theta. We just write it out again. And now we expand this. 4 times 1 over 5 times 3, 4/15 sec squared times tangent, plus, and now the 4/5 times the 2/3, 4 2s are 8, 3 5s are 15, and that integral we've said is tangent, and then we'll just add an integration constant at the end. So we could stop there, or we can just pull out a factor of tangent, because that is a common factor everywhere. And also, I think it's worth pulling out a factor of 15, and that just means we write that as 3/15 and leave the 3 in the brackets. So certainly if we want to verify this by differentiation, I think this makes the job a little bit easier. And that's what I'm going to do on the next slide. So if you haven't done that already, why not use differentiation? Clearly you're going to need the product rule and the chain rule to do this, and a little bit of algebra will be needed too to show that the derivative of this is sec to the power of 6. So what we've done on this slide is we've just used this formula repeatedly, and I think it's important when you're using a reduction formula to think about what you are trying to get down to. You're always trying to get down to an integral which is easier, so we need to recognize what it is. And here, because we were starting with an even power, we're reducing it down to I2, which is very doable. Okay, let's look at this and verify it by differentiation on the next slide. Okay, so this is what we want to differentiate. The integration constant clearly vanishes. We can pull out a factor of 1/15, and we're going to use the product rule, the derivative of this times this, plus this times the derivative of that. So just again, to rewrite it, what I'm saying is the way I like to write out the product rule is this way, this ordering. Okay, so 1/15 is a common factor. Derivative of that is sec squared times all of that bracket, plus 1/15 tan theta times, open a big brackets, the derivative of this. We're using the chain rule. Bring the power in front, 3 4s are 12, reduce the power by 1, sec cubed, multiply by the derivative of the quantity that was raised to the power, so the derivative of secant, and that is sec times tan. Plus, we do exactly the same thing again. 2 comes in front, 2 4s are 8. Reduce the power by 1, that's a secant. Multiply by the derivative of secant, that's sec times tan. And now the derivative of 8 is 0. So what we're going to do is just expand, and the first term here is going to be, well, 1/15 is a common factor, so I'll pull it out. 1/15, open a big brackets. From here, we get 3 times sec to the 6th, plus, and then it's 4 times sec squared is sec to the 4th, plus 8 times sec squared. So that's the first line. The second line, we're going to have 12. Sec cubed times sec is sec to the 4th. Tan times tan is tan squared. Very good. We know the identity we're going to use. Plus 8 times sec is sec squared. Tan times tan is tan squared. And that's 0. So now, we're going to rewrite tan squared as sec squared minus 1. And let's see what we get when we do that. So the first line, I just rewrite 3 sec to the 6th of theta plus 4 sec to the 4th of theta plus 8 sec squared of theta. The second line is going to give us plus 12 sec to the 6th of theta from the sec squared term minus 12 sec to the 4th of theta when it's multiplied by 1. So those two terms correspond to that one. In a similar way, here we get 8 sec to the 4th of theta when from the term tan squared is sec squared here, minus 8 sec squared times 1, so that's minus 8 sec squared. And now we just look at the terms here, and we're expecting to get sec to the 6th, and this is now all in terms of powers of secant, so we expect the sec squareds to cancel, and they do. We expect the sec to the 4th terms to cancel, and here we have 4 minus 12 plus 8. 4 plus 8 is 12, minus 12, they all cancel. Again, you notice I'm using different markings to signal the cancellation in case something goes wrong, and then I can more easily find out where the error was. Okay, so everything is gone apart from the secants to the 6th. There are 3 of them here and 12 of them here, That adds to 15. So we have 15 over 15 secant to the sixth, which is secant to the sixth, the original integrand, and that is exactly what we expected. With that, I'll stop this video.